The choice of carbon capture technology is largely dependent on the conditions where you want to capture the CO2. CO2 Capsol have developed a number of patents on carbon capture utilizing hot potassium carbonate and is now demonstrating the performance at Stockholm XD. We're excited to hear more about the technology, so please welcome Marketing and Communication Manager Tone Bäckstad.
Thank you so much. My name is Tone Bäckstad. I'm the Marketing and Communication Manager of CO2 Capsol, and I would like to thank Bellona, first of all, for inviting us to be part of this conference. A lot of good participants so far today, and I thought about starting off with actually thanking Jim Stian Olsen, who did a really good point there in his presentation of pointing out where we are, where we need to go, and the possibilities that are there for us to actually achieve this if we really want to. We are, as I said, very excited to be here. So let's dive in. My goal is here to try and tell you a little bit more and explain a little bit more about our capture technology, which is maybe not as well known, at least in Norway, as amines and the process that Aker Carbon Capture has. So let's dive in. So, as already mentioned by both Jannike and Jim Stian, carbon capture must increase, and it must 100-fold by over the next 30 years to reach the Paris goals or the UN climate goals. This translates to approximately 5.6 billion tons of CO2, which is almost equal to today's global oil production. That is a huge undertaking, and it will require trillions of euros in investments. We know that we have, and we're quite confident that we have a both cost competitive technology, and it is very energy efficient. This is both based on external studies and calculations that we have performed for potential customers. As it says here on the left, our technology is low on CapEx, but it is significantly lower on OpEx because we use significantly less energy than other comparable carbon capture technologies due to that we have a patented energy recirculation, which is our main patent. And we know from the projects that we have been working on, and especially the ones in Scandinavia, that approximately 50% of the carbon capture costs are related to the use of energy in the carbon capture process. Hence, keeping the energy costs down will help us reduce the costs for carbon capture. And this is where our technology comes in. Since we managed to keep most of the energy that is used for the carbon capture process, we keep that within our system. This results in lower energy consumption and hence lower energy costs, which in turn results in lower OpEx than comparable technologies. As it says here, it's a flexible and scalable solution. It's a so-called end-of-pipe solution where you connect our capture plant to the outlet from the flue gas, or this is to an existing plant, or if you build in parallel with a new plant. Having an end-of-pipe solution and being a standalone unit as our capture unit is, reduces both the risk for expensive modification at the parent plant and also the risks that you might run of having to shut down your parent plant for a longer period of time during installation and construction. What we do, since it's an end-of-pipe solution, you can build the whole unit and then you just connect it to the mother plant as soon as the capture plant is ready. Our technology is based on a chemical capture process, much like amines, which is also a chemical process. However, the solvent we use, hot potassium carbonate, is safe, it's cheap, and it's readily available. And it has been used to capture sour gases in thousands of plants globally in multiple industries for more than 70 years. So this is a really known technology. It has a long history, and as I said, it's a well-known technology, known to be very effective. And what we have done with this technology is that we adapted the technology to use our potassium carbonate to capture CO2 from flue gases. And in addition, we have increased efficiency of energy in the process, which reduces the cost. I will get back to that with a simplified drawing of our technology. On the right-hand side, we state our costs, and we like to be explicit and transparent of the costs of carbon capture. We state the costs of our technology, of how much it will cost to capture 1 ton of CO2, and we do it because we believe, as also Jim Stian mentioned, that the costs are too high. We hope that being totally transparent with how much it should cost and how much it will cost with our technology, we may be able to help reduce the costs throughout the whole value chain, including transport and storage, although that is outside our scope and our core business. Because we believe that getting the cost down will be a major step in getting carbon capture, utilization, and storage deployed on a large scale globally, which is totally necessary to reduce global emissions and climate change. At the same time, I would like to point out that although we bid on the same contracts as our so-called competitors, we do not see them as competition. With the need to increase the carbon capture capacity with 100-fold from today's capacity in just 30 years, there is more than enough for all of us in the carbon capture space. As I mentioned earlier, we like to be explicit on cost and we like to be transparent. And we say that our costs are approximately 25 to 30 euros per ton of CO2. For larger projects and for projects with high CO2 concentrations, the cost will be lower. For projects that are smaller and with lower concentrations of CO2 in the flue gas, the cost will be a little bit higher. At the same time, we can also use a lot of excess heat from the process and bring that back into, for example, a district heating system, which will bring down the costs even further. And we've had some really good studies and projects working on this. Worth mentioning is that in the numbers presented here, that is for carbon capture only, and it does not include liquefaction, intermediate storage, transport, and final storage. So it's the carbon capture cost. And as a rough estimate, just to give you an approximate number of how we see our part as part of the whole value chain, as a rough estimate, the cost for carbon capture with our technology is approximately 25% of the total cost for the whole value chain. And as an example, in a project we are involved in, the total cost for carbon capture to final storage is 90 euros, of which 22 is the cost for carbon capture. The build time for our plant is approximately 18 to 24 months, where the long lead item is the compressor. As already mentioned, the technology has been used to capture sour gases for more than 70 years. And what we have done is then to adapt it to capture CO2. We have also tested the technology in 3 pilot projects for more than 3,000 hours, which have been very successful with an operational uptime of 99% and a capture efficiency of 90 to 95, which is usually the most cost-efficient capture capacity capture capacity. When we look at projects and work together with our customers, we have no definitive 90 or 95%. We look at what is the most cost effective for the client. We can capture more, but that we will most often incur more costs to the project. So being between 90 and 95 is often the sweet spot when it comes to the carbon capture rate. I would like to take you through the history and look back a little bit, because the company is not that old. CO2 Capsol is not an old company, but the history goes back and the technology has been developed for a number of years. It all started out in 2003 with a team of very skilled engineers who were confident that carbon capture would be an important technology to reduce CO2 emissions and to combat climate change. They established a company called Sargas. They were right, but they were also wrong. They were right in the way that carbon capture would be an important technology. However, they were 15 years too early. But again, going back to what they did what I already mentioned. They took a well-known technology. They did some adjustments to make it applicable for capturing of CO2 from flue gases. And the technology they developed was first tested in Stockholm at the coal-fired power plant in Värtaverket. This is where they now have a biomass-powered combined heat and power plant. And this is also where Scandinavia's, as of today, largest carbon capture plant will be installed and up and running in 2025. The company Sargas, they developed patents, they marketed the technology globally, they worked tirelessly to make this a success. But as I said, they were too early. And by 2014, there were no money left. They had spent 40 million euros, and the investors were not willing to invest more money into the company. And they filed for bankruptcy. One of the owners, Einar Lange, was disappointed. He knew the technology was good. He was quite confident that the market for carbon capture would be there very soon. And he kind of saw the contours of the Paris Agreement. Based on this, he decided to buy all the assets and try to establish a new company and give it a new go. He contacted our chairman, Endre Ordingsund, and also our CEO, Jan Kjelland, and he asked them for help to establish a business plan and to get the company up and running. They worked hard to get the company going. And by 2020, they saw that this was going in the right direction, and it was now time to expand the organization and raise capital. And since then, the company has grown, and we see a steady stream of incoming requests. We have by now established ourselves as a serious and important player in the carbon capture space, and we will continue to grow both as a company and with really strong partners globally. This is a very simplified overview of our technology, and for those of you who are technology savvy, this will be a little bit too simplified. This is our end-of-pipe solution using hot potassium carbonate in conjunction with our patented heat recovery. And I would like to draw your attention to the blue arrows. Those are the ones that are the main differentiators between our technology and other comparable carbon capture technologies. And if we start with the blue arrow on the left-hand side, although our process is a chemical process with an absorber and a desorber, much the same way as an amine process, we add a compressor and compress the incoming flue gas to around 5 to 8 bar, depending on the concentration of CO2 in the flue gas before it enters the absorber. And we do this to make the absorption and desorption process efficient. In the absorber, the pressurized flue gas reacts with the potassium carbonate solution, absorbing around 90 to 95% of the CO2. And what happens then is that the CO2 and the hot potassium carbonate solution leaves the absorber. Let me see if I can have leaves the absorber here at the bottom, is transferred to the top of the desorber, where the partial pressure of CO2 is low. This forces the sorbent to release the CO2 to the steam flow, and the CO2 then leaves the desorber at the top here. At the same time, the CO2 lean solution, the hot potassium carbonate, which has now released the CO2, leaves the desorber here. Where is my arrow? Leaves the desorber at the bottom and is fed again into the top of the absorber, and so the cycle continues. This process using hot potassium carbonate to capture CO2 has been viewed as way too expensive and not a viable route due to the high energy demand required to pressurize the incoming flue gas. And flue gases in industrial processes are usually not pressurized, and hence they need to be pressurized to make this process efficient with hot potassium carbonate. And this is where our patented energy recirculation comes in. It's the blue arrow to the right on the drawing. We are able, as I said, to keep most of the energy used for the process within the system. And based on this, our technology is low in energy consumption, as I already mentioned, And it keeps then the cost down per ton captured CO2, since approximately 50% of the carbon capture cost is due to electricity costs. Another key feature of the Capsol EoP end-of-pipe solution is that it can be run on electricity only, the blue arrow on the bottom part there. This has been viewed as a huge advantage to several plant owners, as there is no need for external steam production to run the capture facility, and there is no need for any time-consuming or potentially costly modification of the parent plant. All the steam needed for the capture process and for the system is generated within our system. And lastly, the blue arrow on the top. Potassium carbonate is basically white salt soluble in water, which is mainly used in the production of soap and glass and also used in the food industry. It's safe, it's non-flammable, non-toxic, and it's non-proprietary, which means you can buy it more or less anywhere. And we've seen that the cost for potassium carbonate is approximately 0.3 euros per ton captured. So it's a very cheap solvent. We'd like to draw your attention to the left-hand side first. We've touched upon this already, but as I already mentioned, it's a separate standalone unit which does not affect or influence the parent plant. This means that it can be built totally by itself and then just connected to the capture plant, for example, during a maintenance period. As I said, there are several advantages to this, that you don't need any risky or costly modifications. And also, another good thing about having this as a separate unit is that in the unlikely event that the capture unit shuts down, or you would like to shut it down for a shorter or longer period of time, you can do so without it affecting the parent plant at all. And we have touched upon this, the advantage of being able to run on electricity only. This has been regarded as a great advantage by a number of plant owners that we are in dialogue with. Adding to this, that our OPEX, as carbon capture cost, is low due to the energy recirculation and the possibility to reuse excess heat from the process itself has proven to be of great value to our clients. There's also no reliance on specialized parts to build the capture unit. This is, as already mentioned, known technology used in the industry for several decades, and most components are off the shelf. Maybe without the largest compressors and heat exchangers for very large plants, they might need to be customized. And one single unit can capture around 2.5 million tons per year. The critical component here being the compressor, where the largest compressor on the market as of today has a capacity of 450 kilograms per second. It is also easily scalable with multiple units for larger projects. When it comes to industrial applications for our technology, a year ago, the focus and the industries we received the most requests and inquiries from were primarily biomass and waste to energy. However, over the last year, we have seen more and more requests from the cement industry, which we know account for 8% of the world's CO2 emission. And this is very interesting, especially knowing that some of the large-scale ones, cement plants, have the potential of making a real difference when it comes to reducing CO2 emissions. And seeing this shift that the global cement industry sees the need for, and they want to be part of the solution, and that carbon capture is probably the only option for them to reduce their carbon emissions on a large scale, is very positive. In addition to the cement industry, we see interest from industries like steel, silicon, LNG, hydrogen. And we would say that even though we will be able to capture for lower concentrations and also higher, our sweet spot, I would say, is somewhere between 7 and 25% of CO2 in the flue gas. I would like to draw your attention to Stockholm XD. You probably already know about Stockholm XD, and they have selected hot potassium carbonate solution from CO2 Capsol at their plant. They have a biomass-fired heat and power plant in Värtaverket or in Stockholm. And they are currently running a FEED, a front-end engineering design study, which was awarded to the EPC company Petrofac in June of last year. Previously, Stockholm XD was owned 50% by the city of Stockholm and 50% by Fortum. However, last year, Fortum decided to sell their share to a consortium of long-term financial investors, institutional investors, led by the Dutch pension fund APG. And what is quite interesting with this and positive was that when APG sent out their press release regarding this, I believe approximately 80% of the press release were used to talk about Stockholm XD's carbon capture project, which is very interesting. If you look at the 5 bullet points in the lower left-hand corner, those are the main reasons why Stockholm XD decided to go for our technology and go for hot potassium carbonate. It's the highly competitive economics, the ease of installation of our end-of-pipe solution. It's as I already mentioned a couple of times, a proven technology, widely deployed. Hot potassium carbonate has been used in the industry for more than 70 years. It's very safe, and also the opportunity they get to use a lot of the excess heat and put that into the district heating system. Stockholm XD has run their test facility for more than 18 months now. And what's interesting, I listened to a webinar with the head of research and development at Stockholm XD, Fabian Levin, at one point. And with a smile, he said that when they installed the test unit, he was quite surprised himself that he was just able to push the button, push on, and the test unit started to run, and it has run since then. Although they have decided to go for a large-scale plant, they are still doing tests. And the reason for this is that they are so happy with their test unit that they just want to test every other possibility or any configuration in that test unit, which is very interesting to see that they're doing. It's also interesting to know that it was mentioned here earlier about the EU Innovation Fund. And we are, of course, very happy for Stockholm XD that they were awarded funding from EU's Innovation Fund as one of the 7 companies that got funding or received funding, which is, of course, a huge milestone for Stockholm XD. They will be able to capture 800 tons of CO2 per year, which is approximately double of Klemetsrud and the Norsen plant in Brevik, which is a large plant. It will be, by then, Scandinavia's largest plant and maybe even the largest one in Europe. And Jannike mentioned this, the biomass and the BECCS that when your fuel is biomass, installing and capturing your CO2 will mean that you get negative CO2 emissions. And this is what Stockholm XD will have. Since all of this, what they do is use biomass, they will have 800,000 tons of negative CO2 emissions, which basically means that Stockholm City will be carbon neutral when this plant is up and running at the end of 25. As it says on the bottom here, final investment decision is expected in approximately 1 year from now in Q1 of 23. And lastly, I just want to summarize with a few points that we like to be explicit, as I said, on costs. We want to be able to help drive the costs down in the whole value chain so that we are able to deploy more CCS opportunities and CCS plants globally. It's a standalone unit, minimal modifications, short delivery time. It's a safe hot potassium carbonate, a solvent, and we only use electricity. We can use steam, but it can be powered by electricity only. Thank you so much.
Thank you very much, Tone. As you might have guessed, your cost predictions have sparked some questions online. So please, Tone, join the tap-in platform and join the conversation. And thank you for being with us today.
Thank you.